white phosphorus in a sealed tube, for several days, nearly 507 or 510 kelvins. I'll get red phosphorus, red P. Then again here red phosphorus on heating in a sealed tube, like in an inert atmosphere, in an inert atmosphere, it is heated nearly 803 kelvins. It gives a series of black color phosphorus, just like a graphite series. It gives a black phosphorus. That is called a series of black phosphorus. Allotropic series means different allotropic forms, like just like graphite series. So the graphite like series phosphoruses exist, black. Here series means two types are there: alpha black phosphorus and beta black phosphorus. Alpha and beta black phosphoruses. Two important black phosphoruses, allotropic forms. Again now, particularly here red phosphorus is heated say under this temperature 803 kelvins, particularly in a sealed tube. We'll get the alpha black phosphorus, alpha black P. This alpha black P, it is not oxidized easily in air. It is opaque, transparent in nature, and is generally orthorhombic or monoclinic structure is present. Monoclinical clinic structure or rhombohedral. Same here to get separately, your white phosphorus is heated nearly 473 kelvins. Beta black phosphorus is obtained. So these are the some important allotropic forms of phosphorus. In last class about white phosphorus and red phosphorus explained. Now about black phosphorus, now types alpha and beta phosphoruses, black phosphoruses, two important types. Maybe how do you get alpha black and beta black? Now how do you convert red phosphorus to alpha, white phosphorus to beta? Temperatures very important. Okay, next. After these allotropic forms of phosphorus, next important concept is hydride of phosphorus. Hydride of phosphorus. Here I will explaining hydrides of 15th group elements. Some important hydrides of nitrogen, phosphorus, arsenic, antimony and bismuth given. Here are two important hydrides of phosphorus given to you. That is, one is phosphine PH3. Another one is diphosphine. That is P2O4. Sorry, P2H4, diphosphine. It is the second one is also given least stable hydride of phosphorus is diphosphine. So among these two, one is most important, that is phosphine is most important. So your hydride of phosphorus. First one is phosphine. Your preparation methods. Preparation methods of phosphine, pH3. Important. 2 to 3 important methods are there. One is with white phosphorus. This is the phosphorus P4, that is white phosphorus, is reacted with the alkali solution NaOH plus H2O, 3 moles, and here are 3 moles. On heating, we'll get 3 NaH2PO2 is formed, plus pH3 phosphine gas is produced, prepared. This is white phosphorus is reacted with the alkali solution. This is alkali solution. So the phosphoruses are here 3 are there and 1 4 balanced. The sodium 3 are balanced. Hydrogen atoms are here 6 plus 3 9. Here 3 2s are 6 plus 3 9. Everything is balanced. Its name is sodium hypophosphite. Hypophosphite this is. It is a phosphine. Phosphine it is, yes. So by using white phosphorus, more reactive than compared to red phosphorus, by using alkali solution we can. Then second important method is calcium phosphide. Calcium phosphide formula is Ca3P2 calcium phosphide is reacted with water, or it is reacted with acids HCl. They are the Ca3P2 calcium phosphide and calcium phosphide. That gives corresponding calcium hydroxide, CaOH taken thrice, plus phosphine is formed, pH3 is formed. Now balance it here. 2 phosphines are there, that's why take care of the 2 phosphorus, that's why you take 2 moles. Here are the 3 calciums are there, 3 Ca, 3 moles. Like finally hydrogen atoms are 9 plus 6, 15. So here this is taken twice. 6 plus 6, 12 are there. We want here the 6 moles balanced. Same here, we'll get here 3 CaCl2 calcium chloride plus here the 2 pH3 phosphine gases liberated. Now here balancing 6 chlorine atoms required, that's why take care of the 6 moles balance. These are the 3 important methods to prepare hydrides of phosphorus, that is phosphine. Clear? The obtained phosphine is a colorless, highly poisonous gas. The obtained this gas phosphine, here the pH3 is a colorless, rotten fish, not egg smell, and it is highly poisonous, gas. Now this phosphine, that is pure phosphine, pure pH3 is non-inflammable gas it is, but it is impure pH3 is inflammable, that is inflammable gas it is. When it is mixed with impure means when it is mixed with P2H4 plus IR phosphorus vapors. Diphosphine and phosphorus vapors are mixed with this phosphine, that is impure. That impure phosphine is inflammable in nature. If it is pure, non-inflammable in nature. Very, very important. So the impure phosphine is purified by using iodosin bromide or iodosin iodide. I'll explain how to purify the obtained impure phosphine. Now, just like ammonia, phosphine also a basic in nature, and its basicity explained to you. Now here NH3 is a ammonia, hydride of nitrogen. Phosphine, this is the hydride of phosphorus. Arsine, this is ASH3. Here SbH3, stibine, bismuthine, BiH3. So these are the 15th group of hydrides: nitrogen hydride, phosphorus, arsenic, antimony, and bismuth. Among all these, this is the more basic in nature. Here the basic strength is like already in introduction about hydrides of 15th group elements explained is more basic. That is due to the presence of lone pair, and it also contains lone pair, also more basic, but is more basic because from nitrogen to bismuth size increases, atomic size increases, donation capacity of lone pair of electrons decreases, basic strength decreases. This is the order like this. So anyhow, just like ammonia, phosphine also a basic in nature because on phosphorus here the two lone pair of electrons are there. These are ready to donate. That's why here it is electron pair donor. Electron pair donor is a Lewis base. Just like ammonia, it is also Lewis. But its basic strength is less than compared to ammonia because size increases. Around phosphorus here the 3 hydrogen covalent bonds are there. Now here the in phosphine, due to the presence of this lone pair ready to donate, it is reacted with the hydrogen bromide HBr. In hydrogen bromide, it forms the H plus plus Br minus. Here H plus contain a vacant orbital. These lone pair of electrons donated to this. It forms one coordinate covalent bond, that is PH4Br minus. This is the plus and minus. So are this is the phosphorus, and around phosphorus 3 covalent bonds are there, and it contains one lone pair of electrons. These lone pair of electrons are ready to donate hydrogen ion proton. It forms a coordinate bond. It is linked with the Br minus. It is a salt. Phosphonium bromide. It is called a phosphonium. Phosphonium bromide it is. Just like ammonium bromide. We know ammonium bromide formula is NH4Br. It also ionizes, it gives NH4 plus plus Br minus is there. Just like ammonium bromide, phosphonium bromide, that is PH4Br. Now it ionizes, it gives phosphonium ion PH4 plus plus Br minus is there. This is. So due to the presence of this lone pair on phosphorus and phosphonium molecule, phosphine molecule, it reacts with HBr hydrogen bromide or hydrogen iodide like. It forms corresponding phosphonium halides, phosphonium bromide. That phosphonium bromide again ionizes, it gives phosphonium ion plus Br minus. Now the obtained impure phosphine is reacted with HBr hydrogen bromide. It forms phosphonium bromide. Now it is reacted with alkali solution, like KOH, like this alkali solution. I guess the corresponding the obtained phosphonium bromide is reacted with the alkali solution. Here the aqueous alkali solution. It forms pure pH3 phosphine gas plus your KBr plus water is formed. Now, in this manner, we can purify the impure phosphine gas. So, the first, how to purify this phosphine, impure phosphine means in this manner. Now, first it is reacted with, it is pH3 is reacted with HBr under all these conditions, basic nature and donation capacity. It forms a phosphonium bromide. It is reacted with alcoholic KOH solution. It gives pure phosphine. It is pure. Now, by using this simple chemical reaction, we can easy to estimate, we can easy to say, yeah, the phosphine also acts as a Lewis base, which is ready to donate pair of electrons. Basic strength of phosphine. Now here phosphine also here reacts with hydrogen iodide. It gives the corresponding phosphonium iodide, just like Hi. So here one of the most important question is here. The pH3 is a phosphine and here pH4 plus is a phosphonium ion. Phosphonium ion it is a phosphine molecule. Phosphine molecule. Once we can observe in this phosphine, around phosphorus 5 valence electrons are there. Out of 5 valence electrons, one is electron pair, that is LP, lone pair, and 3 are the covalent bonds with 3 hydrogen atoms. Sigma bonds are 3 are there. This phosphorus undergoes sp3 hybridization based on hybridization concept. Bond pairs are 3, lone pairs are 1. That's why total 4 are there. 1 plus 3, 4. That is sp3 hybridization. But due to the presence of this lone pair and bond pair repulsive forces, its geometry is pyramidal geometry. Pyramidal. And its bond angle is 107 degrees. Whereas in case of phosphonium ion, your phosphonium ion is formed between phosphine plus proton, that is H plus. It forms like pH3 and electron pairs donated to this. It forms a phosphonium ion. Means around phosphorus 5 valence electrons are there. 1 valency electron pair is donated to the H plus ion like this, and remaining 3 are the covalent bonds. Now this pair is involved in a chemical bonding, that is a coordinate bond. Coordinate bond, that is also a covalent bond. Here there is no LP electrons. They are involved in a chemical bonding. Sigma bonds 1, 2, 3, 4 sigma bonds are there. 4 sigma means sp3 hybridization. If it is sp3 hybridization, it is a tetrahedral geometry. And its bond angle is here 109 degrees 28 minutes. Why it is 109 degrees 28 minutes means there is no lone pair and bond pair repulsions. Absence of these lone pair and bond pair repulsions, bond angle is as it is 109 degrees 28 minutes. Whereas in case of phosphine, its bond angle is reduced from 109 to 107. That's why based on the last some questions. Why the bond angle of phosphorus and hydrogen in phosphine is less than phosphonium ion? Reason is in phosphine, due to the presence of due to lone pair and bond pair repulsive forces, repulsions, bond angle reduces from 109 degrees to 107 even though it undergoes sp3 hybridization. And also geometry changes from tetrahedral to a pyramidal. So they'll compare between these two, phosphine and phosphonium ion, very, very important. Then simple uses of pH3, very, very important. It is used in your home signals. In home signals, along with pH3, they'll use calcium phosphide like Ca3P2 or calcium carbide CaC2 mixture. So the mixture of phosphine, calcium phosphide and calcium carbide, either anyone, it is used in a Holmes signal, L is silent, and also in a smoke screen. In smoke screens, we can use this phosphine. Easy to fire. To get some signals, we can use in detection of some signals in sea navigation, that is home signals, as well as in household purpose home screens to find out easy to fire where it is takes place, easy to catches the fire and it creates some important flames. By using that, we can identify easily problems present in that particular area. That's why phosphine is used in home signals as well as smoke screens. Okay, this is about phosphine, hydrides of phosphorus. Clear? Just based on this structure, observe how the last questions. Just 1 minute. The next one is very, very important concept is halides of phosphorus. Halides of phosphorus. Generally, phosphorus forms two important halides. One is PX3 and another one is PX5. Two important types. These are two types of halides. Your X stands for halogens. Your halogens, your fluorine 17th group elements, chlorine, bromine, iodine or astatine like. So the direct phosphorus react with the halogen molecule, it gives trihalides. PX3 is trihalide and PX5, that is pentahalides. Phosphorus trihalide and phosphorus pentahalide, two are there. Here we can take general in our syllabus like PCl3. This is PCl5. Here the PBr3, PBr5 like this. Here the PI3, PI5 like this. While explaining in organic chemistry, in haloalkanes and haloarenes, your PCl3 and PCl5 are PCl5, PBr5 are At the time of situation, we can prepare in situation, in situ, given in NCERT textbook. Preparation of haloalkanes by using alkyl halides like phosphorus pentachloride, phosphorus trichloride, PCl3, PCl5 like PBr3, PBr5, PCl5. At the time of situation, we can prepare directly. Yeah, the white phosphorus react with halogens. It gives corresponding trihalides as well as pentahalides. So here first one is pentahalide. Pentahalides like phosphorus pentahalides. Yeah, the two important methods are there here. That is, we can take PCl3 preparation method. Directly, here the P4, that is white phosphorus, that is more reactive than compared to red phosphorus. Directly react with chlorine on heating, will get PCl3, phosphorus trichloride. Now here the 4 phosphorus are there, better you take here the 4 moles. Now how many are there here? 12 are there. Here how many are there? Only 2. That's why we want here 6, 2 that's 12 balanced. Trichloride, tribromide, in this manner we can prepare. And also it is prepared by using here white phosphorus is reacted with SO2Cl2. Sorry, SOCl2. This is called thionyl chloride. Very, very important formula it is, because in haloalkanes and haloarenes, one of the most important process, Darjan's process is there. In Darjan's process, when alcohols reacted with thionyl chloride in the presence of HCl, it gives corresponding haloalkane, that is chloro. Now the white phosphorus react with SOCl2, it gives corresponding the PCl3 phosphorus trichloride plus S2Cl2 is formed. It is called sulfur monochloride. It is sulfur monochloride, S2Cl2. Sulfur monochloride means like S bond S, the Cl and the Cl. On sulfur, each sulfur, the 2 lone pairs are there. And on chlorine atom, the 3 lone pairs are there. Out of 7, 1 is bonded with sulfur. This is sulfur monochloride. Balance it. Take care of the 8 moles. Then SOCl2 plus P4 molecule. We'll get here PCl3 phosphorus trichloride here 4 moles. Then again here we'll get SO2 gas, sulfur dioxide gas. Here 4 moles required. 8 balance 6 and here take 2 moles. Now these are the 2 important preparation methods of phosphorus trichloride. Now phosphorus trichloride, general phosphorus trichloride, phosphorus tribromide, whatever it in organic chemistry, very, very important it is. The obtained PCl3 is a generally oily liquid, oily yellow colored liquid substance. Now the obtained phosphorus PCl3, phosphorus trichloride, easily hydrolyzes, it gives corresponding phosphorus acids. Now the obtained PCl3 is a oily liquid. It is oily liquid substance. Here the PCl3 on hydrolysis react with water, it gives corresponding H3PO3 phosphorus acid. Plus here corresponding HCl is formed, hydrochloric acid is formed. Now here anhydride of phosphorus acid, generally anhydride of this or hydrolysis of H3PO3 Hydrolysis of PCl3 with water, it gives corresponding H3PO3 phosphorus acid. It is orthophosphorus acid, and hydrochloric acid is formed. Now the 3 chlorine atoms are there here, only 1 phosphorus. So totally are the 3 required, like balance. Here are the 3 HCl. So are the phosphorus trichloride on hydrolysis, it gives corresponding phosphorus acid, that is orthophosphorus acid. For organic chemistry, this is one of the most important reagent compound it is. Here the PCl3 reacts with organic compounds containing bond COOH or bond OH groups. It gives corresponding organic chlorinated or halogenated compounds. Like compounds containing COOH group means like CH3COOH is a carboxylic acid, or R bond COOH is a carboxylic acid. It is reacted with PCl3, it gives corresponding halogenated compound, organic compound, plus your H3PO3 is formed. Means here are 3 chlorine atoms required, that's why take here the 3 moles. Now here the 3 moles, it is balanced. It is called a acetyl chloride. It is called acetyl chloride. Now it is a phosphorus acid. Similarly, common example for this we can write here. PX3 is reacted with carboxylic acids. It gives 3 moles of the R bond COOH, COX plus here the H3PO3 is formed. This is R bond C double bond O bond X acetyl chloride. In first year, based on this Friedel cross alkylation and Friedel cross acetylation, we can use acetyl chloride, CH3COCl. Similarly, just like carboxylic acids, we can use alcohols also, like ethyl alcohol. Very important preparation method of chloroethane. Ethyl alcohol like C2H5OH reacted with PCl3, it gives C2H5 bond Cl plus H3PO3 is formed. Here Cl only 1, but here 3 are there. That's what is multiplied with 3. Then here we'll take 3 moles of ethyl chloride or chloroethane. In haloalkanes and haloarenes in organic chemistry, first unit haloalkanes and haloarenes, first chemical properties of alcohols. When it is reacted with PCl3 or PBr3, whatever it, alcohols converted into haloalkanes. Okay. After these 2 important chemical properties and general points, structure of these PCl3. In this structure of PCl3, phosphorus trichloride, phosphorus valency we know that is 5. Valency electrons 5 are there. 2 are like 1 pair. Remaining 3 are the unpaired. These are reacted with 3 chlorine atoms like. Now on chlorine, each chlorine 7 valency electrons are there. Out of 7, 1 is donated to phosphorus. It forms like 3 sigma bonds. 1 lone pair and 3 sigma bonds are present around phosphorus. That's why it undergo sp3 hybridization. sp3 means it is a pyramidal structure. Why it undergoes a pyramidal structure we know? That is due to LP and BP repulsions, lone pair and bond pair repulsions. And its bond angle also reduces. Bond angle is 107 degrees. This is the structure of PCl3, phosphorus trichloride. Last only one is there, that is phosphorus pentachloride. Same, similar methods, almost all same. Slight variation, number of moles increases. Same explanation, but very, very important is structure of PCl5. Guarantee question, already 2 to 3 times asked in objective. That is PCl5 in a solid state as well as in a liquid or a gaseous state. Structure very, very important. Okay. So here, next one is phosphorus pentahalide. That is PX5 in that pentachloride, phosphorus pentachloride. PCl5. Just like PCl3, here also first preparation method is with the white phosphorus. Here the white phosphorus is reacted with the excess Cl2 chlorine on heating. We'll get PCl5. Same PCl3 also will get it. That is limited. Here we can take some excess chlorine, will get PCl5. Now this is the 4 moles because phosphorus 4 white phosphorus. Here the 20 chlorine atoms required. That's why I take 10 moles of chlorine. Then PCl5, phosphorus pentachloride, will get it. Similarly, white phosphorus is reacted with here SO2Cl2. It is called a sulfuryl chloride. Thionyl chloride and sulfuryl chloride. A difference. SO2Cl2 is a sulfuryl chloride. SOCl2 is a thionyl chloride. That is the difference in oxygen atom. Then here it gives the same, here the PCl5 plus SO2 gas is liberated. Now here the 4 moles of PCl5. Now 4 balanced. Now here the 20 chlorine atoms required. That's why I take here the 10 moles. Then finally here the 10 SO2 sulfur dioxide gas. Yeah, these are the 2 important preparation methods of PCl5, phosphorus pentachloride. Now here the properties. Properties of this, just like phosphorus trichloride, pentachloride is a crystalline solid, white crystalline solids. And on hydrolysis, here the PCl5 on hydrolysis, it forms like phosphorus oxychloride, POCl3 and HCl. Here are the 2 moles. This is called a phosphorus oxychloride. That phosphorus oxychloride again on hydrolysis with the water, it gives like H3PO4, phosphoric acid. Phosphoric acid plus HCl is formed. This is very, very important. On hydrolysis of phosphorus pentachloride, we will get phosphoric acid. Whereas PCl3 on hydrolysis, it gives corresponding phosphorus. This is the difference. Here the PCl3 reacted with Yeah, H2O, it gives corresponding H3PO3. OUS acid plus HCl is formed. Are the 3 moles or the 6 HCl, like your 6 moles of 6 plus 6, sorry, take 6 moles. Now we'll get total 6 HCl phosphorus acid. It is a phosphoric acid. That's the difference between PCl3 acid, PCl5 is ic acid is formed. Phosphorus and phosphoric acids. Just like trichlorides, pentachlorides also reacts with organic compounds. Your PCl5 reacts with organic compounds containing COOH group and OH groups. It gives corresponding carboxylic or halogenated compounds. See here, your PCl5 react with carboxylic acid, acetic acid. This is CH3 bond COOH react with PCl5. Gives your CH3 COCl, product is same in both the cases, plus here the POCl3 phosphorus oxychloride plus hydrochloric acid is formed. So here your CH3, I'll write here only to compare. CH3 COOH is reacted with PCl3. Gives here the CH3 COCl plus H3PO3 is formed. Difference is here 1 mole, here 1 mole. Here all here 3 moles are there, that's why I take here the 3 moles. Here 3 moles. Now both the cases product is same acetyl chloride, acetyl chloride. When it is reacted with the PCl5 with the same organic compound, it gives phosphorus oxychloride as byproduct, whereas in case of PCl3 it gives a phosphorus acid. That is the difference. Yeah, both are 1 mole and 1 mole only, but here 3 and 1 mole. Based on this, in objective they'll ask questions, number of moles based. And what are the byproducts obtained? Now here in both the cases carboxylic acid structure is like this, like C double bond O bond OH. Your cleavage takes place between carbon and oxygen. This OH group come out. So that cleavage between carbon and oxygen only, not between oxygen and hydrogen. Here cleavage takes place. Just like carboxylic acid, your second reaction is alcohol, C2H5 bond OH. React with PCl5, it gives C2H5 bond Cl plus POCl3 plus hydrochloric acid is formed. Same preparation methods of haloalkanes, chloroethane, chloropropane, depending upon the type of alkyl group. These are the some important properties, chemical and physical properties of phosphorus pentachloride. Okay. Similar examples, both trihalides and pentahalides. But your important thing is structure of PCl5 is very important. Structure of PCl5 is already given in object examination number of times. There are 2 to 3 important points are there. Heading is structure of PCl5, phosphorus pentachloride. Once we can observe here in PCl5, central element is phosphorus. In this phosphorus, number of valence electrons are 5 are there. neon 10, and here the 3s2 and 3p3. 3D is available. This is the ground state electronic configuration. Here 2 electrons and here 3 electrons. D orbital is vacant. This is the ground state electronic configuration of phosphorus. Whereas in case of phosphorus pentachloride, around the phosphorus 5 chlorine atoms are there. That's why compulsory 5 sigma bonds means 5 unpaired electrons are required. That's why 1 electron from its outermost orbit exit from lower energy level to the higher d orbital, higher energy level like d subshell. Here 1 electron, that is 3s1, 3p3, 3d1 it is. Here it is 1 3s1 electron, here 1 electron, and here 1 electron, like 1 s orbital, 3p orbital, and 1 d orbital undergo intermixing against 5 sp3 d1 hybrid orbitals. With these 5 chlorine atoms are bonded, like here the 5 sigma bonds are formed. Your sp3d is nothing but that is trigonal bipyramidal structure. But this trigonal bipyramidal structure is generally in liquid or in gaseous state. Liquid or gaseous. Very, very important. What is the structure of PCl5 in a liquid or gaseous state means? Trigonal bipyramidal structure. Hybridization is sp3d, whereas in solid states, it exists as your PCl4 plus 1 and PCl6 minus 1 it is. Very, very important. In examination, generally, to confuse the children or the students, they'll give instead of this PCl6 power plus 1 and PCl4 minus 1 this is. In examination, they'll give like this also. But this is wrong interpretation, wrong explanation, wrong structure it is. Now in solid state, it exists as like this. Here it is a positive charge is there, that is the cationic like complex. It is minus 1 is the anionic complex it is. In solid state, cationic, that is tetrahedral geometry is there it is. Very, very important. Tetrahedral form is here the PCl4 power plus 1. And it is anionic is octahedral shape. 2 are there, octahedral structure. That is PCl6 power minus 1. Very, very important. Cation and anion, octahedral and tetrahedral structures are very, very important. This is wrong. Number of times asked here based on this PCl5, based on solid state and liquid or the gaseous state. In liquid or the gaseous state, trigonal bipyramidal and hybridization is that. Whereas in solid state, it exists as like PCl4 and PCl6. One is cationic form and the one is anionic form. In cationic form, it is a tetrahedral shape. In anionic form, it is a octahedral shape. Very, very important. And based on this, one of the most important structure around phosphorus, once we can observe here 5 bonds are there with the chlorine. These 5 bonds again are divided into 2 different types. Among 5 sigma covalent bonds, 2 are the axial bonds, 3 are the equatorial bonds. This is the phosphorus. Now this is generally equatorial and it is axial like axis. This is the Cl. 7 valence electrons are there out of 7, one is bonded with this phosphorus. Similarly, remaining 4 chlorine atoms react with the central element of phosphorus. It forms 5 covalent bonds, like 5 sigma covalent bonds are formed. Sigma. Among these 5 sigma covalent bonds, are the 3 sigma covalent bonds. These are equatorial and these 2 are axial. Here to your axial bond length PCl Cl, axial bond length is 204 picometer, that is axial bond length are 204 picometers. That axial bond length is more than compared to equatorial. Here 2 such a PCl axial bonds are present, whereas remaining these 3 are here. These are generally 2 slight variation is there. Now here the 3 PCl equatorial bonds are present. Such a equatorial bonds, 3 sigma covalent bonds are present. Here bond length is slightly less than the axial bond length. Here 202 picometers. Why here axial bond length is slightly greater? This axial bond length is greater than equatorial bond length. The reason is in axial, due to the presence of more repulsive forces, more electronic repulsions between axial bonds and axial bonds, bond length increases. That is very, very important point. This is the structure of PCl 5 in aqueous, in liquid state and gaseous state, as well as in solid state. Based on guarantee, we'll ask one question. Okay. Last, only one important concept is there, that is oxo acids of phosphorus, and 1 or 2 important points about the phosphorus. Tomorrow I'll complete oxo acids of phosphorus. Then I'll start a new topic, that is in P block elements only, 16th group elements, oxygen family. Okay, almost all 15th group completed. Better you read today only, complete 15th group elements. Take care.